Okay, we want to go through this worksheet, and this will be in several videos so as to not make any one video too long. But we're going to start with number 1, and this is going over the fundamental theorem of calculus part 1, which let's come over here and remember what that was. So if we have g of x is equal to the integral of a up to x of f of t dt, then g prime of x, the derivative of the integral, is our function evaluated at that right endpoint. We also have the chain rule version, and that is if we have g of x equal to a up to some function of x, f of t dt, then the derivative of g this time is our function evaluated at that right endpoint, h of x, then times the derivative of h of x. So that's what we're going to be utilizing here in question 1. So we'll try to write them over here on the side. So 1a, we're looking for the derivative with respect to x of the integral from a up to x, it happens to be 0, of our f of t dt. And so by the fundamental theorem of calculus, that's just going to be this function evaluated at that right endpoint. So this is equal to the square root of 1 plus x squared. Perf. All right, b, very similar. 1b, we're going to be taking the derivative with respect to y of 1 up to y, 3x squared dx. Now, a minute to talk about these variables. It doesn't matter what we call what, as long as this variable right here matches this one, and we're taking our, when we're applying fundamental theorem of calculus, and that the one inside is not the one here and here. Okay, so that's all that matters. So the derivative of the, one way to say this is the derivative of the function of this right bound on our integral is, so it's going to be our inside function evaluated at y, so 3y squared. Now, 1c changes things up a little bit because we have to make an adjustment. So remember, this is our rule, a up to x. If we want to now take the derivative with respect to z of z to 5, so our variables match sine of y squared, and this one is different, that's all that's required, dy. The problem is this is in the wrong order, right? We need to have a up to z, not z up to a. But we use the rule that of integrals, properties of integrals, that we can flip the bounds as long as we change the sign. So really we're going to be looking at the derivative with respect to z of the negative of 5 up to z sine of y squared dy. And that negative can come all the way out, and then you just apply the fundamental theorem of calculus. So it's going to be the negative of sine of z squared. Not so bad. So A, B, and C, done. We're going to have to do the same kind of thing here in part D. So 1D is ddw. See how we're just throwing around different variables? ddw of w up to negative 2 secant of z cubed dz. Just do a really quick check. This variable matches the one on the bounds, and the one inside is different. All right, we got to first flip this so that it's a to w as opposed to w to a. So this is the negative of ddw of negative 2 up to w of secant of z cubed dz. Now we just apply the theorem. So it's the negative of secant of w cubed. Easy peasy. Okay, now we're going to get to use the chain rule version here. So this is no longer just a single variable. That's ddv of the a up to v squared. So this is the chain rule version. So we're going to come over here to 1e. And rewrite it over here. So it's ddv of 7 up to v squared, natural log of w squared plus 1 dw. So since this is now not just the same variable, it is the same variable, and those variables have to match, but it's not just v itself, it's a function of v. So then the chain rule applies. So it's going to be equal to the inside function evaluated there, so the natural log of v squared squared, so v to the 4th plus 1, times the derivative of v squared, 2v. Easy peasy. Let's do it again. So f, so we'll write it over here, 1f is taking the derivative with respect to u of 3 up to u cubed plus u, tangent of v dv. Again, this is straightforward, so let's just check again. This variable matches the variable in our bounds. It's a up to, so we don't have to flip the order, and it's a function of u and not just u itself. So when we take the derivative, it's going to be the inside function, tangent, evaluated here, u cubed plus u, times the derivative of u cubed plus u. So 3u squared plus 1. Not so bad. All right, so that's f. All right, now let's come over here. So let's look at g for a minute. So g, our variables match s and s, but that's a function of s, and it's in the wrong order. So we have a couple things to do. We have to flip it and then apply the chain rule. So let's come over here and rewrite it. So 1g, I guess it was. Yeah, dds of the square root of s up to, I think it was 6, u squared over u squared plus 4. U squared over u squared plus 4 du up to 6. So step 1, we want to flip it so it's a up to our variable. So this is equal to the negative of dds of 6 up to the square root of s, u squared over u squared plus 4 du. And now we're ready to apply the theorem, but note that this is not just s, but a function of s, so we're going to do the chain rule. So it should be equal to the negative of the inside function evaluated there, so the square root of s squared over the square root of s squared plus 4, and then times the derivative of the square root of s, which is 1/2 s to the negative 1/2. If you wanted to clean it up just a little bit, you would have s on the top, s over s plus 4, and then times 2 square roots of s on the bottom. Don't simplify unless you're told to. Yeah. All right, so that's 1g. Now we have another thing we have to do here, and that is where I don't have an a at all. But I can split this up at an a and have 2 integrals. So let's rewrite this. Let's see if I can come down here and see it at the same time. So 1h, we're going to be looking at ddr of the integral from cosine of r up to sine of r, and the inside function is e to the s squared ds. So just do a quick check. This variable right here matches the ones on the bounds, and the one inside is different. That's key. All right, we don't have an a, and we need to have an a up to a function. So we're going to split this up. First thing we're going to do is write this as cosine of r up to 0 of e to the s squared ds plus 0 up to sine of r e to the s squared ds. And we're going to be taking the derivative of that with respect to r of both sides. Now we have one more issue, and that is that this one right here is in the wrong order. So we're just going to flip it. So we get the negative ddr of 0 up to cosine of r e to the s squared ds plus regular ddr of the integral of 0 up to sine r e to the s squared ds. All right, and now we just apply the chain rule. So the derivative of this thing is going to be the inside function evaluated there. So e to the cosine squared r negative times the derivative cosine of r, which is a negative, so now we have a positive, sine of r, plus e to the sine squared r times the derivative of sine of r, which is positive cosine of r. That's it. It's not so bad. Lastly, let's do it one more time. So we're going to have to split this up into two and flip one of them. All right, so let's write it right here. So 1i is d dt of square root of t squared, inverse sine of r dr. Okay, so first step is to split this up into two. So we're going to be looking at d dt of square root of t up to 0. You can pick any one you want, as long as it's defined on the inside. Sine inverse of r dr plus ddr of 0 up to t squared, sine inverse of r dr. Before we do it, we got to flip this one. So that's the negative of d dt of 0 up to the square root of t, sine inverse of r dr, plus this one just stays the same, ddr of 0 to t squared sine inverse of r dr. Now we're ready to apply the fundamental theorem, chain rule version. So it's the negative of the inside function evaluated at that right endpoint times the derivative of that right endpoint. So 1/2 t to the negative 1/2. Plus, same thing here, inside function evaluated at the endpoint, so sine inverse of t squared times the derivative of t squared, 2t. That's it.